In chemical reactions, molecules of reactants are taken apart into atoms, and these atoms are used to build molecules of products. Therefore, when reactants are completely transformed into products, the total number of atoms of each element in the products must be the same as the total number of atoms of each element in the reactants. As we have already seen, this condition is satisfied once the equation of a chemical reaction is balanced. Molar ratio coefficients in a balanced chemical equation show the ratio between the amounts of different reactants that must be taken in order to completely convert reactants into products. They also show how much of each product is made for a given amount of reactants. Let's consider the example of the methane combustion reaction to see how one can predict the amounts of products made in a chemical reaction if one knows the amounts of reactants. The balanced chemical equation for the combustion of methane is CH4 gas plus 2O2 gas is converted to CO2 gas plus 2H2O gas, water vapor. This equation tells us that if we take one molecule of methane that consists of one carbon atom and 4 hydrogen atoms, and 2 molecules of oxygen that consist of 2 oxygen atoms each, we will have just enough atoms of these 3 elements, carbon, hydrogen, and oxygen, to build one molecule of carbon dioxide that will require the carbon atom and 2 oxygen atoms, and 2 molecules of water that will require 2 hydrogen atoms and 1 oxygen atom per water molecule. So the balanced chemical equation is like a recipe. By looking at the molar ratio coefficients, we learned that to burn one methane molecule completely, we need 2 oxygen molecules. And when we react the methane molecule with these oxygen molecules, we get 1 carbon dioxide molecule and 2 water molecules as a result. Taking more than 1 methane molecule and 2 oxygen molecules per methane molecule would allow us to make more carbon dioxide and water molecules. However, the number of carbon dioxide made as a result of this reaction would always be the same as the number of methane molecules used. In other words, there would always be 1 carbon dioxide molecule per methane molecule used, a 1-to-1 ratio of the numbers of methane to carbon dioxide molecules. There would also always be 2 water molecules made per methane molecule used, a 1-to-2 ratio of the numbers of methane to water molecules. We could also say that there would be 1 carbon dioxide molecule made per 2 oxygen molecules used, a 2-to-1 ratio of the number of oxygen molecules to carbon dioxide molecules, and that there would be 2 water molecules made per 2 oxygen molecules used, a 2-to-2, which is the same as a 1-to-1 ratio of oxygen molecules to water molecules. If we were to take more than 1 methane molecule, say 3 methane molecules, and 2 oxygen molecules per methane molecule, so that would be 6 oxygen molecules total, then we could make 3 carbon dioxide molecules, 1 per every methane molecule, or 1 per every 2 oxygen molecules, and 6 water molecules, 2 per every methane molecule, or 1 per every oxygen molecule. If we were to burn 1 mole of methane with 2 moles of oxygen, we would make 1 mole of carbon dioxide and 2 moles of water, and so on. Thus, we can always say how many molecules or moles of each product we can make from a given number of molecules or moles of reactants. However, when we get reactants, we don't usually know how many molecules or moles we have in our sample. What we can easily measure is the mass of reactants. Furthermore, we are often interested in the masses of the products, not the number of molecules or moles in them. Luckily, we already know how to convert grams to moles and moles to grams. If you have forgotten how this is done, please rewatch the video on the molecular mass and molar mass. Let's say that we want to find the mass of water that is formed when we burn 48.129 grams of methane. We know that for every 1 mole of methane we make 2 moles of water. So how many moles of methane is 48.129 grams of methane? We can find the number of moles of a compound by dividing its mass by its molar mass. A methane molecule is made of 1 carbon atom and 4 hydrogen atoms, so the molar mass of methane is the molar mass of carbon, 12.011 grams per mole, plus 4 times the molar mass of hydrogen, 1.008 grams per mole, and that comes to 16.043 grams per mole. The total number of moles of methane is then 48.129 grams divided by 16.043 grams per mole, and that comes to 3.0000 mole. Thus, 48.129 grams of methane is 3 moles of methane. For every 1 mole of methane, we make 2 moles of water. So when we burn 3 moles of methane, we should get 6 moles of water. To convert the number of moles of water to the mass of water, we need to multiply the number of moles of water by the molar mass of water. The water molecule is made of 2 hydrogen atoms and 1 oxygen atom. So the molar mass of water is 2 times the molar mass of hydrogen, 1.008 grams per mole, plus the molar mass of oxygen, 15.999 grams per mole, and that comes to 18.015 grams per mole. The mass of the produced water that we get in this reaction is 6 moles times 18.011 grams per mole, and that comes to 108.09 grams. When you are doing these calculations, please make sure to keep track of the units and the number of significant digits for all quantities. In summary, to calculate the mass of a product that is made from a given mass of a reactant, we need to take the following 4 steps. First, convert the mass of the reactant to the amount that is the number of moles of reactant. Then use the molar ratio coefficients in the balanced chemical equation for the reaction to figure out how many moles of the product is formed per mole of the reactant. Then calculate how many moles of the product are formed for the number of moles of the reactant that is used. And finally, convert the amount, the number of moles of the product, to the mass of the product. As an exercise, I recommend calculating the mass of carbon dioxide that is formed in the methane combustion reaction if we start with 48.129 grams of methane. Also, you can try finding the mass of oxygen that is used to burn 48.129 grams of methane, and to verify the law of mass conservation for this reaction.